Hey, geometry students, in this lesson we're going to be talking about your favorite three-dimensional figure and mine, the cone. That's right, we are going to be talking about cones. A cone is a three-dimensional figure with a circular base, a curved lateral surface, and that lateral surface connects the base to a single point above the base, a vertex. Now, interestingly, this is a very specific type of cone we're going to learn called a right cone because the altitude of the cone makes a right angle with the base. But actually, this vertex can be anywhere. It could be over the circular base, or it could be way outside the circular base as well, and it's still a cone. We'll be talking about that in just a second. So, as I've alluded to, the base of the cone is the circular face. In this case, it's at the bottom. Technically, the base of the cone doesn't have to be the bottom of the cone, but we usually draw cones so that the circular base is at the bottom. The vertex is the point opposite the base where the lateral face connects to. And then the altitude, now, this is important. It's perpendicular to the base. It's a perpendicular segment from the vertex to the plane containing the base. So, most cones that you're used to seeing will have the vertex over the base. So, it's actually perpendicular to the base itself when you drop the altitude. However, some cones, remember, have this vertex like shifted way off to the side. So, it's not over the circular base anymore. In that case, we would say the altitude is from that point to the plane, perpendicular to the plane that contains the base. Now, what we're looking at is a right cone, one in which the altitude has an endpoint on the center of the base. That's how we define it. If the altitude goes from the center of the circular base to the vertex, and it makes the right angle like it should, that makes it a right cone. An oblique cone is any cone that has an altitude that doesn't intersect the center of the base. So if we start moving around the vertex point to a different spot, so it's not right above the center of the circular base, now we have an oblique cone. Slant height is exactly like slant height we learned in the past. It's just the height. There's a good way to define it here. The distance from the vertex to the a point on the edge of the base. Okay, so we're going along this outer surface here, slanting down to the base. And then lastly, the radius of the cone is this radius of the circular base of the cone. All right, now we have three equations we're going to be learning about in this lesson. First of all, we're going to talk about how to calculate the surface area of a cone. Well, okay, this equation is kind of dumb because it's exactly what you would expect it to be, but it doesn't tell you how to calculate any of it. Okay, it's the total surface area cone is given by the formula surface area equals the lateral area plus the base. Well, wait a second though. How do I calculate the lateral area? How do I calculate the base? Base is easy. The area of the base is pi r squared. The lateral area is going to be pi times the radius times the slant length. Okay, so to calculate the lateral surface area of a cone, we need to use the slant length, pi times r times L. And then lastly, the volume of a cone, that equation is 1/3 times the area of the base times the height. And that goes, and when I say height, I really mean altitude, okay? Because that will work for any cone, whether it's a right cone or an oblique cone. You can use that formula. All right, let's take a look at some practice problems. Basically, we're going to practice using these equations. So first of all, we need to calculate the lateral area of a right cone with a radius of 2 feet and a slant height of 7 feet. The lateral area. Well, lateral area is just pi times the radius times the slant height or the slant length. Okay, so letter A is really easy. It's just going to be pi times a radius of 2 feet times a slant length of 7 feet. That's it. That's how you calculate the lateral area. We don't have to worry about pi r squared or anything. We only do that if we're doing a circle. So let's go ahead and do this. Pi times 2 times 7. So we're just going to use a calculator. Pi times 2 times 7 gives us 43.98. All right, and let's check our answer. 43.98 is correct. Let's go on to letter B. So in letter B, we have to calculate the total surface area of this cone in the diagram. That's pretty straightforward and easy to do. So calculate the surface area. I need to make sure I add together the lateral area plus the base. The base is the easy part. Okay, so I look at this cone. It's got a radius of 3 meters. So that means the base is just going to be pi times 3 squared. Okay, pi times 3 times 3. I'm just going to write it out as pi times 9 because 3 squared is 9. Okay, we have to add to that the lateral area. Remember, the lateral area is pi times the radius times the slant length. Well, pi times the radius is easy. What is the slant length, though? All right, I'm going to move over here. Let's calculate the slant length of this. Slant length is going to be, well, okay, hold on. This looks like a right triangle here. The altitude, the radius, and the slant length make a right triangle. So this is going to be 3 squared, or 9, plus 8 squared, or 64, equals the lateral, the slant length squared. Okay, so I need to do the square root of 9 plus 64, or the square root of 73. What I'm going to do is I'm just going to plug that right like that into my equation, the square root of 73. Okay, so it's going to be pi times 3 times the slant length, which is the square root of 73. And then I'll round my answer from there. Pi times 9. Okay, so let's punch this into a calculator. Pi times 9 plus, and let's see, what do we got? Pi times 3 times the square root of 73. 108.79. It rounds up to 108.8. When I add this all together, 108.8. This is an area, so it's going to be in square units. This is going to be meters squared. Okay, let me just get this all in one line, and let's see if we did this right. 108.8 for letter B. Yes. All right, on to letter C. In letter C, we have to calculate a volume. Volume is going to be this equation, 1/3 the base times the height. So it's going to be 1/3 times the base of a cone. All right, so it says calculate the volume of a right cone with a height of 10 inches and a radius of 6. Well, the base is going to be the area of the circle that has a radius of 6, pi r squared. Pi times 36, which is 6 times 6, right? Then I need to multiply that times the height of 10 inches. Now, I'm going to punch this into a calculator, but first, can I simplify this? I can multiply 1/3 times 36 and change that to 12. And then I can multiply 12 times 10 and change it to 120. So this is actually just going to be 120 pi. I can punch that into a calculator much more easily. 120 times pi. There we go. And I get 376.99 or 377. In this case, it's a volume, so it's going to be in inches cubed. And let's go ahead and see if we got this right. 377 inches cubed. There we go. Now, lastly, the area of a traffic cone is about 70 centimeters high and has a diameter of 20 centimeters. A diameter 20 centimeters. Oh, interesting. What is the volume of the cone? Okay. So I don't care about the volume. I actually need to find the area of the base, which requires the radius. So it's going to be 1/3 times the area of the base, which is pi times the radius squared. The radius of, so if diameter is 20, that means the radius is 10, and the radius squared is 100, times the height, which is 70 centimeters high. Okay, now I can't really simplify the 1/3 with anything because nothing divides by 3 perfectly, but I can multiply 70 times 10 to make 7,000, just to get one fewer number to punch in my calculator. 1/3 times pi times 7,000. Let's go ahead and do that. 1/3 times pi times 7,000, and I'm left with 7,330.38. Now this is going to be in centimeters cubed because it's a volume. And let's just check to make sure we got that one right. And that's how you do these sorts of problems. You should be ready to do the problem set for next time.